Before we begin, there will be one tutorial session after the lectures today. So that's from 5 to 7 UK time, and there will be a morning tutorial session. So tomorrow from 10 to 12. So there's a double tutorial session between today and tomorrow, so that you are aware of it, although it's in the timetable. All the information you can see it on Mural about lecture notes, exercises, announcements, and so on. You can disconnect the subtitles in your Zoom session if you want to. Sometimes they get if they are on, they can be a bit annoying or entertaining, depending on your taste. But you can always switch them off. Also, if you want to ask any questions, you can raise your hand. But then the usual announcement that you probably know, that you will be recorded. So if you prefer not to, you can always use the Q&A box. I'll keep an eye on that, or the chat, but preferably the Q&A, and I'll pass these questions onto the speakers at the end of each talk. I think that's more or less all the announcements. So today we have 3 lectures, which are a continuation of what we started yesterday. So we'll have from 2 to 5 Philip Trin, and then 3 to 4 Kemal, and 4 to 5 Daniele, continuing on the material that they started yesterday. So without any other thing for me to say, I would like to pass to the first speaker of the session. So please.
Thank you very much. Just before we start, a quick note to the students. I mean, I've been really impressed by how everyone's worked during the tutorials, so do keep up the good work. My initial design for this talk, I've decided to scale it back a little bit, because what I noticed during the tutorials is that some students really struggle a bit with calculations. And so in this lecture, I'm going to go in detail into some of the calculations. So I know there are a lot of senior people in the audience, but this is mainly for the students to learn about some of these techniques. Okay, so this is the second of 3 lectures on exponential asymptotics for physical applications. The first one was yesterday by John Chapman, and I'm doing the second one on fluid mechanics and applications to waterways. And then John King will run the anchor leg on multiple scales. And we're going to start off with just doing a big review of what John taught you yesterday on applications to nonlinear differential equations. The basic idea is that you have a nonlinear ODE, or maybe even a PDE, but I've written an ODE here in terms of y and its derivatives. And you do the usual thing, which is to expand it into a perturbative expansion in powers of this small parameter epsilon. In doing so, you notice that there are singularities in the earlier terms, and these singularities have the effect that they will magnify, and that produces usually factorial overpower divergence, but not always. But in most cases, the divergent form that you can expect is a factorial overpower. Why do you do this? Why do you try to find this late orders divergence? Well, that's all explained by the next few steps. The series diverges, so you try to truncate the series after n terms, and now our goal is to try to find this remainder, which you expect, you're hoping to find is exponentially small if you truncate optimally. That yields a equation for the remainder. You can linearize the equation for the remainder, and crucially, it's forced on this right-hand side by a term that involves an order epsilon to the n error, because you've truncated after all, and so you have this order epsilon error. So this is really the key part of this slide, which is to recognize the fact that as epsilon tends to 0, the optimal truncation point n tends to infinity, and therefore this gives you a crucial relationship between the remainder that you're trying to find and the late order terms. And that's sometimes why when people do this exponential asymptotics business, they say you're decoding the divergence. You're using the divergence to tell you something about the remainder term. The remainder term will involve those exact components of the divergence that you predicted earlier. So the a here and the chi here, the singulant chi, which appears now in the exponential. And as Chapman explained, your goal is to now find a differential equation for this Stokes multiplier, this S of Z. And in doing so, you'll find this boundary layer phenomena across the Stokes lines. There's a criterion, almost a universal criteria that you can apply to find the locations of those Stokes lines, which is, in this case, the imaginary part of chi is 0 and the real part of chi is greater than or equal to 0. So equal phase and maximal dominance, okay? And this, just to keep in mind, this is a problem where the base series, this y, it has an exponential e to the 0. Otherwise, this Stokes line condition would involve measuring the relative singulance between two exponentials, okay? But for the problem that I'll present here, this is the Stokes line condition. So this is the methodology that, that was laid out in lecture 1. Okay, so now I'm gonna tell you some interesting history about water waves, okay? And I think it's suffice to say the study of wave structure interactions. This is a classic, historically important subject that continues to have great scientific and industrial importance. But crucially for us, right, the key is that there's some exponential asymptotics here to be done, and it links to observable phenomena. So that's the nice thing about studying applications of exponential asymptotics to water waves. Not only are they kind of fundamentally scientifically important questions, but they relate to observable and computational phenomena. This is a picture from J. Scott Russell's famous 1845 report on waves, just to show off, the variety of behavior that you can have in wave structure interactions. Everything from overturning waves to vorticity to white cap forming on the surface and ripples of all sorts of different kinds. So the kind of the main traveling wave waves here, and then the small scale ripples here. So this is something that you hope to explain. Okay, so now what does this relate to what does it have to do with exponential asymptotics? Well, in the public lecture, John Chapman kind of noted this low-Froude paradox that was first highlighted by a naval architect, Francis Ogilvie, in '68. So I'm going to tell you about this low-Froude paradox. The situation that you want to keep in your mind is that you've got two-dimensional flow over this rigid, this obstacle here that has some length scale L. You're looking at steady state flow. U is the incoming speed of the stream. And if you fiddle around with the dimensional quantities, you will come out with a governing non-dimensional parameter, which is the crucial parameter, this Froude number here. So this parameter here measures the relative strengths of inertial and gravitational effects. This is the epsilon. So we're going to be looking at the limit, the epsilon tends to 0, low Froude, or you can think of it as low speed flows. And this is 1968, unpublished. I mean, it's a technical report from the University of Michigan by Francis Ogilvie, and he notes, in attempting to solve a problem involving the motion of a body near a fluid-air interface, one generally linearizes the boundary conditions at the free surface. This is a matter of sheer necessity, for otherwise there's little hope of solving anything. He goes on, generally, if the first linear approximation is a poor one because the perturbations are too large, there cannot be very much hope of improving it with higher order terms. A remarkable exception to this rule appears to have been found by Salveson in '68. This is another unpublished report. We have shown that under certain conditions, the second order solution dominates the linear solution. It appears paradoxical that it should be necessary to include higher order approximations at very low speeds, for the total disturbance becomes smaller and smaller as speed is reduced more and more towards 0. One should expect the assumptions required for linearizing ought to become steadily more nearly valid as the free surface deflection decreases. Instead, the problem appears to become more nonlinear. So it's a little bit cryptic what he's referring to, and it's not quite clear what he's referring to. He's referring to the singular nature of the epsilon to 0 approximation and how something funny seems to be at work when you try to develop wave approximations to that problem. And I won't say more about that, except that over the next few decades following Ogilvie's '68 paper, a number of people tried to go into this area of developing low Froude approximations, and similar cryptic statements appear in the literature. Here we have someone, Tulin, who wrote in 2005, very recent in comparison, does an asymptotic low speed theory of thick ships really exist? And if so, what is its correct form? And then another 1983 paper by Tulin. The most important comment to make is that for a given epsilon, no matter how small, this so-called low speed theory is not valid for sufficiently low speed. It is a theory valid for low, but not too low speeds. Really confusing what that means. How can something be valid for low but not too low speeds? Okay, so this is just my example of a little expose of the confusion that existed within this area. And I don't want to diminish all the contributions from people from the 70s and 80s. A lot of people developed theories to try to explain these low speed waves or low fluid waves, but none of them had that some of the necessary equipment of exponential asymptotics, the explanations from Stokes lines and the Stokes phenomenon that we know now today. So this is what I want to present to you. And this talk is going to follow some of the work by Chapman and Van den Broek from 2006. Okay, so the situation that we're going to look at is flow past, it's a model problem, two-dimensional potential flow past the body of a ship. So this is the figure on the left here is the rear side of the ship, the stern of the ship that you've modeled as a semi-infinite body. Okay, and you're interested in trying to find this potential, which relates to the velocity of the flow. Okay, now in this talk, I'm mainly going to be working with, just for simplicity, sigma equal to 1/2. So that corresponds to a rectangular stern here. So sigma relates to the angle of the single corner. Okay, so the task is for you to solve Laplace's equation within the fluid. You have no penetration conditions on the solid and fluid boundary, so this kinematic condition. And then you also have a dynamic condition. This is known as Bernoulli's equation on the free surface. You notice the epsilon appears in here. So there are three reasons why this is a tough problem to solve. It's a very hard problem to solve. The first reason is that the geometry is quite complicated, right? The second reason is that the free surface is unknown. You don't even know where the free surface is, so it must be solved as part of the problem. And the third reason is that the Bernoulli's equation is nonlinear, and that causes a lot of difficulties in developing analytical methods. So you have to take some kind of approximation. You have to look at the limit, for instance, of epsilon tending to 0. Okay, so there's a second trick to solving these problems, these potential flow problems, and the trick is to invert the formulation. I've already introduced to you the potential function phi, and this potential function has a harmonic conjugate called the stream function psi. The stream function is 0, or sorry, it's constant along surfaces. So I can set the stream function to be 0 from A to B to C to D. So this is what you see on the picture on the right here. A, B, C, D. In the phi psi plane, the boundary A, B, C, D has been mapped to the real axis. Okay, and so you think of things in terms of this W, so-called complex potential, and crucially, rather than thinking of W as a function of Z, this is what we usually try to think of phi as a function of X and Y, you invert that and you think of Z as a function of phi and psi. And the advantage is that if you invert this formulation here, then you solve in a domain which is very simple. It's just the lower half plane. Okay, so that's the first step to kind of reformulating this problem in a tractable way. The second step is that you may not want to be working with Z, X and Y, just trying to solve for X and Y. Rather, you'd like to solve for the velocity components. It just makes the formulation a little bit easier. So for this talk, I'm going to be working with a streamlined speed Q in an angle theta. So that is to say, if you take a particle of fluid in your system and you follow it along the streamline, it'll have some angle, we call that theta, and it'll have some speed, we call that Q. So these will be the two unknowns in our problem as a function of the complex potential W. Okay, right, so the governing equations are as follows. You firstly have Bernoulli's equation posed in terms of your Q and theta variables. So this is the nonlinear equation that was causing us a lot of grief. And secondly, there's a way to repose in essence, Laplace's equation. So rather than solve Laplace's equation within the bulk of the fluid, which is a two-dimensional problem, it's difficult, right? The trick is that you apply Cauchy's theorem and you integrate around the boundaries. So in this case, A to B, if I go back to my previous picture, you integrate from A to B to C to D, and then a little semicircle that you send off to infinity. And that reduces the problem to essentially determining that Q and theta should satisfy a boundary integral equation. So you have Bernoulli's equation and a boundary integral equation, which is integrated on your solid surface, which runs from -infinity to 0, and then your free surface, which runs from 0 to infinity. This little dash here is the Cauchy principal value. This dash in the integrand, if you've not encountered it before, all it is that this integral is singular when this variable of integration phi here is equal to the original phi. So you subtract out the little indentations and you integrate to epsilon left of this phi, and then from epsilon all the way to infinity. Okay, so that's the Cauchy principal value. Now, you know, for this integral, you know the values from -infinity to 0. If I go back to this picture here, I know that the angle of the ship is 0 from A to B, and then it's either pi sigma, or in the particular case that we're looking at, pi over 2 from that point on. You put that into the integral, and now you've reduced it down to an integral equation that needs to be determined from 0 to infinity. So just to be very clear, just so everyone's on board, you're looking for unknowns q and theta as a function of phi. These are equations along the free surface when psi is equal to 0. Phi ranges from 0 to infinity, and you assume that there's a stagnation point at the connection between the solid boundary and the free surface, and you assume that the waves are traveling towards the right. The second condition is not so obviously necessary. And that's it. I should say, by the way, that the stagnation point assumption is not obvious. It's not obvious that you should be imposing a stagnation point, but I'll leave it at that. Okay, so I want to we can do the most basic thing and just look at what happens when epsilon is a small number. If epsilon is a small number, you see sine of theta is equal to 0, so therefore theta is equal to 0. So this tells you that when the speed is very small, that has the effect of basically flattening out the free surface at leading order, or the other way of thinking about it is that gravity is infinitely strong and it presses down on everything. This is what's known as the rigid body solution, or rigid lid solution, or the double body solution. I'll tell you why double body in a second. You can then derive the leading equation for Q naught, and it gives you this. So if I plot that profile, this is what I have on the right. Notice that Q is 0 at the connection between the solid boundary and the free boundary, and then it tends to 1, tends to uniform flow downstream. So that looks all very good. If you are wanting to go back to physical space from Q and theta, you can integrate certain relationships for that, and you can recover the streamlines of the flow. So ignore everything in the upper half plane for now. The lower half plane is that leading order solution we had before, where the free surface, which runs from where the mouse cursor is here in the center to the right, that's now been flattened out, and the body is on the left at that point. You'll notice that if I integrate these relationships and I try to solve for the streamlines, I'll also predict that there's a mirror image on the right. And that's why it's sometimes called the double body flow, because for this leading order approximation, it's equivalent to flattening out the free surface and then putting mirror points about that axis corresponding to the structure. Okay, let's now talk about numerical solutions. I want to give you another perspective of how to solve these problems, and just for us to be a little bit more familiar with working with this formulation. Okay, there's a very simple numerical algorithm to solve this problem, and I'll explain it as follows. So the first thing is that you're going to come up with an initial guess for theta. So for instance, I could just set theta to 0 because I know when epsilon is small, theta is near 0. The next step is I'm going to distribute a series of mesh points that run from 0 to a large number. So here phi 1 through phi n. And in addition to that, I'm going to distribute a series of midpoints between those indicated with the red squares. Okay? So the reason why I do this kind of main point, midpoint is that it's a bit of a cheat that allows me to integrate this singular principal value. If I integrate over the main points, for instance, phi 1 through phi n, and I evaluate at the midpoints, I can avoid those singularities. It's not a very accurate scheme, but it works for our purposes. You can come up with more accurate schemes for resolving this principal value integral. Okay, so the boundary integral gives us n-1 values for qi to the midpoints of q using the values of theta. Bernoulli's equation gives us n-1 equations. And we have a system of n unknowns, and you can close the system with the condition at the origin. Okay, so now I'm going to flip. Now, if this is going to work, I'm going to flip to MATLAB, and I'm just going to show you what it's like to just solve this. You can even do it in 23 lines of code that I've done. It's really compressed code, but you can see this. I mean, you can read it over on your own time, but I set out the mesh points and I solve Newton's method for the differential equation. Okay, I can run this. Let's have a look. This is pretty fast. It's only 500 mesh points, and the value of epsilon here is 1. And we look at the picture. Here's the picture that results. So the full numerical solution is given in solid, and the dashed line is our leading order asymptotic solution. So very clearly, the leading asymptotic solution doesn't capture any of those free surface waves. The waves are quite large in this case, and so that's the question. How do you find those waves? You can argue just similar to the arguments that John Chapman had presented yesterday, that you would not expect wave contributions at any subsequent order. If they didn't appear in the very first order, because of the way the singular differential equation occurs, you're not going to expect an oscillatory component in the subsequent orders. So already you have the slight intuition that these are exponentially small, these waves are exponentially small. And if I was an experimentalist, I would go and try to measure these amplitudes and I plot them as a function of 1 over epsilon. I do some semi-log plots and I try to extract out that exponential dependence in preparation for the asymptotics to come. Okay, all right, so let's go on. Right, so now I'm going to show you how to do the analysis, and it's going to use exactly those techniques that we learned yesterday, that John Chapman taught yesterday, okay? Before we do that, we have to allow our governing equation to work in the complex plane. So currently, our governing equations, which are written here in white and in yellow, one white for the Bernoulli equation, yellow for the boundary integral equation. This is for phi being a real valued independent variable, right? But we want to allow phi now to be complex value. We do this in anticipation of the fact that we know there are probably going to be singularities in the complex plane. Okay, so we can set phi to be phi r plus I phi c if you like, and now we're going to consider phi to be complex. We're also going to do a slightly confusing thing and send phi to w. So I'm going to relabel the complex version of phi with the previous complex potential. Okay, either this confuses you or it doesn't, but it's important for you to remember that you're operating not with physical flow field variables. The W is not the one that corresponds to the physical phi and the stream function phi. It corresponds to an analytic continuation of the free surface quantities. And then now Q and theta will be complex value. So you take Bernoulli's equation, and Bernoulli's equation is very easy to analytically continue. You just change the phi to a W, and you just treat this as an initial value problem, if you like, allowing you to walk all over the complex plane. The boundary integral equation is a little bit more difficult to work with, but essentially, you're interested in taking this phi here on the left and then popping it off either into the upper half plane or in the lower half plane. And in doing so, you produce the version to the right here. Notice the integral on the right here is no longer has a dash through it. It's no longer principal value because W here lies in the upper half plane. In this case, I've moved it into the upper half plane and I'm integrating along the axis. And if you don't believe that this is the analytic continuation, you can just send W back onto the free surface and you'll pick up a residue contribution, which will cancel with this I theta and return you to the original dashed integral. Okay, so at the end of the day, this is the formulation that we're going to be spending the next couple of minutes working with. We have Bernoulli's equation for Q and theta, and we have a boundary integral equation here. Now, in what follows, I'm going to write this boundary integral with this Hilbert notation. So I've called it H hat. So H hat is my, you can call this boundary integral the Hilbert transform. This is the Hilbert transform of theta, where W is the independent variable. I use a hat here just to remind myself that it's complex, that W is complex. Okay, right. So what were the steps that we taught you yesterday? The steps is as follows. You start off setting Q and theta to be its regular perturbative expansion. You find the early orders. then you try to write down the order epsilon the n terms. And this is a thing that I want to kind of help the students a little bit with, because everyone's a little bit confused. Which terms do I keep at order epsilon the n? This is a nonlinear problem. It's difficult to see what you should be keeping and what you shouldn't be keeping. Once you know which terms to keep, you try to put in your factorial over power ansatz, and then you try to determine some of those components that allow you to characterize the divergence of those late order terms. Okay, so we're going to try doing this on the blackboard. And it's either going to go very wrong or it's not. Okay, so in order to speed things along, I've written out all the necessities at the very top here, and hopefully you can see what it corresponds to. I'm going to use white for Bernoulli's equation. I'm going to use yellow for the boundary integral equation. We're going to substitute our two expansions of Q and theta in, and the very first few orders are easy. I have a little cheat here of the expansion of the nonlinear terms of the sine theta and the log Q, and this is just something that you can work out in your own time. So if you remember yesterday, well, when Chapman did his talk, he talked about an f of phi on the right-hand side, and that was Taylor expanded. It's the same thing. Our f of phi here is either sine theta or log of Q. Okay, but we need this little cheat just to help us along a little bit. The order 1 expression is very easy to see. As we said, you can set epsilon equal to 0. You have sine of theta equal to 0, so theta is 0. And I have Q naught is equal to W over W plus 1. So already you see that there are two singularities, one at the stagnation point at W is equal to 0, and one at the what previously corresponded to the corner of the stern at -1. Okay, then you can go to order epsilon, and there it is. Okay, now the thing that you want to pay attention to is this first equation here, Bernoulli's equation. You notice that theta 1, the next order that I need, depends on the derivative of Q naught. And this is basically the trend for any singular perturbative problem, that whenever you find a subsequent term, you're differentiating the previous terms. So any singularity that appears in the previous terms will then be magnified. You end up adding to the power of that singularity as you go further and further down the hierarchy. Okay, right. So now we want to do the order epsilon to the n terms. And that's where it begins to get a little bit hard. And I'm going to do yellow here. I'm going to do the boundary integral first, because there's a very important simplification that it provides. Okay, so I go to the log Q here and I look at my little cheat sheet, which tells me which terms I need. So I'll write that down. So at order epsilon to the n, I need a Qn over Q naught minus Q1 over Q naught squared, Qn minus 1, and if I like, I can also write plus order here Qn minus 2, just so you know what I'm dropping in that expansion. Okay, I'm going to then have an I theta, so that plus I theta n like that, and on the right hand side, I just have the Hilbert transform. This is part of the order 1 expression. The Hilbert transform, this h hat of theta n, like so. Okay, so now there's a very important simplification that you do when you do these kind of boundary integral problems for potential flow, which is that this guy is actually exponentially subdominant. And there's not an easy way to explain at this point why you get to assume that. So I'm just you have to take it on faith. So I'm going to claim that this is exponentially subdominant. Well, I can give a hint of the reason why this is the case. As n tends to infinity, you're interested in the limit, the late order terms n tends to infinity. I give a hint of why that's the case. Well, the hint is that basically the Hilbert transform, this h hat, is integrated along the axis, along the free surface. But the singularities lie away from the free surface. And it's because of that fact that the integration domain is further away from the singularities means that this guy is exponentially subdominant. But it's quite difficult to see at this point. What you do is you try to solve the problem making this assumption, and then you go back and you see, was that assumption actually valid? Okay, so this basically just gives you an equation for theta n. So I have theta n is, I move everything, this guy over the right-hand side and divide by my I, and that is equivalent to just multiplying the left-hand side by an I, like that. Okay, so I've got one equation now for my theta n, and I can substitute this one into Bernoulli's equation and try to get this equation for Qn. Okay, and that's the harder bit to do. Right, so I'm going to go to white now, and for Bernoulli's equation, I have to do the expansion of the quadratic. So I have to put into my series into the quadratic and into the derivative expression. And the trick is basically, well, there's kind of two tricks to doing these derivations. The first trick is that you only usually need the first two orders. So you only need the leading order as n tends to infinity, and you need the correction term, just like you do when you do WKB analysis. And the second trick involves the indices and the derivatives, but I'll explain that in a minute. So you basically start off with the highest indices. So you have a 2 q naught qn when you expand that first one, times a q naught prime from the derivative term. And then I'm going to start decreasing this index n to n minus 1 and then increase this index here. So this is a plus 2q1 qn minus 1 q naught prime plus dot dot dot. And I'm also going to need those order epsilon. And I made a mistake here. The mistake is that should be an n minus 1 and that should be an n minus 2, because if I need order epsilon the n terms of this first term, I need the order epsilon to the n minus 1 terms from the quadratic q squared q prime. Okay, so I need the next term I need is a q naught squared times a q n minus 1 prime. And I'm also going to need the next one, that q naught q1 times a q n minus 2 prime. And plus dot dot dot. So you'll notice that basically I started off with the high indices for q squared and the low indices for q prime, and then these are the first two terms, and then I went to the high indices for the prime, and I started with the low indices, and you just decrease them in that way. And you'll also notice that I only started writing 2 terms from each, because I only think there's going to be 2 terms that I need. Okay, so then this is equal to, and then you go to our little cheat sheet here, and then you write down the expansion for the sine. So here are the relevant terms that you're going to be needing for the sine term there. So the first one will be a minus cosine of theta naught, will just be a minus 1 because theta naught is 0. And then theta n, but I know what theta n is here. Okay, so I'm going to put that in over here, and that has the effect of negating everything here. So that's a minus iqn. I should have done this in yellow, but it's too late now. Plus iq1 over q naught squared, qn minus 1 plus dot dot dot. You'll also notice that the next order contribution I wrote down here is theta n minus 1, which we would typically need. It's a little bit maybe near the edge of the screen, but sine of theta naught is 0, so you don't actually have that contribution. Okay, so now basically you want to identify what you think will be the leading order contribution and the next order contribution. And the trick there is that you treat your indices and your derivatives kind of on equal footing. You know that when you have a gamma function expression, we're going to eventually put in our factorial over power ansatz, right? That's the method, into these expressions. And so if I have an index of n, then the factorial will be greater than if I have an index of n minus 1. On the other hand, I know that if I take a derivative of the factorial over power expression, I'm bringing a factor of n up to the top because of the denominator. And so that's why n minus 1 prime would then be treated as equal footing with qn. So you think of your an index shift of minus 1 as equivalent to a derivative here. So I think that this one here will be leading order, and I think that this one here will be leading order as well. This qn minus 1 prime. And then after that, I think this will be second order here, or the next or first order if you like. In the limit that n tends to infinity, I'm going to need this one as well. This is an n minus 2 plus 1 from the derivative, and so that should be of equal footing to qn minus 1 here, and I'm going to need this one here, and I'm not going to need this one here. Okay, so we've identified what we think are going to be the crucial terms. Hopefully you can see, and I've not been standing in front of the screen all the time. You can see now which are the crucial terms. So the next trick that I'm going to tell you is basically we're going to rearrange these things, and then we're going to put it into a way which will make substitution of the factorial over power ansatz a little bit easier for us to deal with. Okay, so my trick, my philosophy is basically move everything to the left-hand side, and I'm going to divide out by the qn. I'm going to kind of combine different qn's and then divide out by what I think is the leading term, and then that just makes substitution of the factorial expression a little bit easier. So the first one I'm going to write down is that one there. So you have a q naught squared times a qn minus 1 prime, and I divide out by the qn. The next one will be this one here. I have a minus I over q naught, but I don't need to divide by anything because I've already divided by the qn, so that should be just a 1 here. The next one here will be a qn minus 1. So I have a 2q naught prime times qn minus 1, and I think there's another one over here, and that should be a plus, by the way, because it's been moved to the left, and I have a minus here, minus I q1 over q naught squared, like that, and I have a qn minus 1, and I divide out by a qn like that. Okay, and then the very last one that I need is this 2q naught q1 qn minus 2 prime over qn plus dot dot dot. And I'll put that into braces like I've been doing with all the other ones. Okay, and there we are. We're expecting that the dominant balance will be between this one, and that all the other terms will then be involved with the next order contribution. Okay, and so then the next step is for you to substitute the ansatz that you think is going to satisfy this factorial over power ansatz. And in this case, it's just a standard 1. So we're going to let now qn twiddles q of w, an unknown function of w, times your factorial of n plus gamma over chi of w to the n plus gamma. And just like we showed you in the previous lecture, you're going to take derivatives of these and try to simplify the expression. So for instance, you're going to have a qn prime here. You take a derivative, the derivative of the denominator comes up. So I have a minus chi prime times a q, and then I'll have an n plus gamma times a gamma function of n plus gamma here over a chi to the n plus gamma like this, plus 1, sorry, like that. And then the trick is that you'll notice that this thing here, by properties of gamma function, is gamma function of n plus gamma plus 1. So that was this derivative and index correspondence I referred to earlier, and I'll also have a derivative of the q prime term, plus q prime times gamma function of n plus gamma over chi to the n plus gamma, like that. Okay, and then you do that as many orders as you need. In this case, you actually don't need to go very far. You only need one derivative. But for a higher order problem, it gets more annoying. One of the exercise questions, I think, is a 4th order problem. So students in yesterday's tutorial were having to work out 4 derivatives of this, which was a little bit painful. Okay, now I'm going to show you a different trick of doing it. Just how do I do it with Mathematica? So if I now, let's see if this will work. The other way of doing it is that you just use Mathematica for things. And I can, in Mathematica, I can put in my my different expressions, my factorial over power expression for Q. I can put in the indices, and then I can try to compute the ratios. By the way, that trick I explained to you before, dividing out by the Q, this was just so you can actually do these simplifications a little bit more easily in Mathematica, because when you try to simplify ratios of factorial functions, it's a lot easier than trying to simplify the gamma function itself. Okay, so you define our 3 ratios that we showed on the board, and then you just do a series expansion in the limit that n tends to infinity. So the very first ratio, as we expected, is order 1, and then the other terms will be order 1 over n and order 1 over n. Okay, so you can even do it pretty easily with Mathematica once you've identified which terms are relevant. Okay, so let's try to find one of the relevant functions here. Let's try to find the chi. We're not going to find the q, and I won't have time to discuss the gamma. But this follows a very similar methodology to the one that was done yesterday. So you can go there for additional details. But I want to just give you the flavor of how this is all done. Okay, so we know that the leading order contribution will come from 1 and 1 here. And so when I substitute in my ansatz, this one here will produce a minus chi prime. So I'll have a q naught squared times a minus chi prime. And then this one here will just have the usual 1 in the back there. and that's equal to 0. So that's at order 1 over n. This is at order 1. This is your order 1 dominant balance as n tends to infinity. So now you can solve for this chi and then integrate it. So here's your chi is equal to the integral from a w star to a w of I over q naught cubed, and I'll be a little bit more some dummy variable here like that. Okay, so by assumption, this singulant function is the thing that generated the divergence. So this w star will be chosen to correspond to the one of the singularities of the leading order problem, the -1 or the 1. Okay, and the next thing you would do is then you go to order 1 over n and dot dot dot. And when you go to the order 1 over n, you use the various ratios we found. You're going to find a differential equation for big Q, and that will allow you to solve for it. Okay, and so that's basically the end of that Blackboard presentation. This is kind of what you would emerge with. So there's our factorial over power ansatz. Okay. And we just found the chi component here. This is the crucial singulant expression, and the q can be solved for. It can always, you won't necessarily always be able to solve for the q function. You have to leave it as a differential equation. In this case, you can actually solve for it, and it involves this prefactor lambda, big lambda. And so at the end of the day, we've determined the big Q, we've determined the chi. The two things we've not determined of this late orders behavior is the gamma here and the lambda expression. Now the gamma you can find basically by matching to the thing that generated the singularity. So there was a discussion about this in the question period of the last lecture, which is that one simple trick is you just set n is equal to 0 and then you match with the necessary singular behavior of q naught. The lambda expression here, this one is much more devious. It's often very difficult to get this lambda. What you have to do is you have to rescale near the appropriate singularity and develop the inner equation, and to develop a series solution of the inner equation and to solve that recurrence relation that it involves. Most of the time, for most of the applied mathematical problems that we're dealing with, we don't actually care too much about the value of that lambda as long as it's not 0, okay? And I'll say a little bit more about numerical checking of some of these relationships in a moment. Okay, so we've determined our late order terms, and then now this is a big slide, but actually the point of this slide is just to reiterate the fact that the Stokes smoothing procedure, so this procedure where I optimally truncate the theta, optimally truncate the q, and attempt to develop equations for the remainders, that typically is a universal procedure. And so you substitute this into the differential equation, you develop your L of Rn is equal to the right-hand side, or L of Sn is equal to the right-hand side, and you substitute in a multiple of the homogeneous solution, which you'll notice here, again, involves the big Q and the chi that you found before. There's this correspondence between the WKB form that you see here for the remainder and the late order ansatz that we used before. You optimally truncate and you localize near the Stokes line. So you write down, you do a change of coordinates so that when R is positive, and this theta is equal to 0, you're right on the Stokes line. And then you attempt to look at the differential equation for this prefactor A as you cross that Stokes line, as you rotate around the Stokes line from the negative theta to positive theta. And in doing so, you're going to predict that there has to be a jump of 2 pi I over epsilon to the gamma. And you can put this back into the full expression for the remainder and predict the resultant waves that form. The last comment I'll have on this slide is that you've predicted a complex exponential, an imaginary component for this q epsilon, this exponentially small wave as you cross the Stokes line in the upper half plane. By reflection principle, because the solution is expected to be real on the axis, then you expect to also add the complex conjugate, and you could have equally done the analysis for the Stokes line in the lower half plane. Okay, let's say a few words about the Stokes lines, because it's a crucial quantity, right? So the Stokes line, as we said, is predicted by the location where chi, the imaginary part of chi that we found, is 0, and the real part of chi is positive. And we can just do it in mathematics. Yes, here we go. So we can just do it in mathematical. We put in our Q0 expression here. We can put in our chi expression and integrate it. And in this case, you can actually integrate it exactly in closed form. It's not always the case that you can do that. And then you can try to plot contours of this function. So here I'm plotting in red the imaginary part of chi equal to 0. So along this, there's a singularity at -1, which corresponds to the corner of the ship. And there's a Stokes line that emerges, or an equal phase line that emerges from that, these sets of lines. And then you need to verify in which region of the plane is the real part of chi positive, right? So if I go to these contours, this one's 0, this one's 0.81. This is the real part. The colors give you the real part. And so I notice the numbers are getting bigger. So that tells me that the Stokes line goes in the positive upper half plane and it loops around. This here on the right, this axis, this positive real axis, is your free surface. And therefore, there is a point across the free surface where you're expecting an exponential to switch on. And those are exponentially small waves that people have been looking for many years. Okay, so one can do numerical and asymptotic comparisons of this problem. You can try, the dots here give you the numerical solutions of the full nonlinear problem, and I can try to match that with my asymptotics for different angles of the stern. That's a nice little fun exercise for you. I should point out by this graph, the gradient of this graph, the way I've plotted it, involving a logarithm of the amplitude at the top and then a 1 over epsilon on the right here, you're expecting this gradient to be approximately straight in the limit that epsilon tends to 0 as you move towards the right there. And you can see that it is straight. So that is basically a confirmation of the chi component of your analysis, the e to the chi over epsilon, e to the minus chi over epsilon, right? And as I mentioned earlier, actually verifying some of these predictions is pretty difficult. It's actually quite hard to verify the Q function in front, or hard to also verify the epsilon to the gamma algebraic dependence on epsilon. And all bets are off for even trying to verify that prefactor that we said was very difficult to obtain. So there's a very interesting problem when you try to do exponential asymptotics for physical problems, which is that you predict certain quantities and computationally or experimentally, you may never be able to check whether your analysis is actually right or wrong if you're looking for independent verification. And that's kind of a difficult, that's why the problems are often very difficult. Okay, now the original Chapman and Vandenbroek 2006 study did it for flow over a step in a channel that you see here. And you can do those types of problems as well. This is a piecewise linear geometry flow over a step. And all it involves is an additional conformal mapping to change the relevant domain for the step to the upper or lower half complex plane. So most of these water wave problems, two-dimensional potential flow water wave problems over piecewise linear bodies, we can do pretty well, okay? I want to say two important comments about the figure here that you see. The first comment is that even though the Stokes line we predicted, we kind of did this analytic continuation process, and you have the Stokes lines in the complex plane, you have switching across Stokes lines, right? There's a correspondence between the analytically continued plane and real space, which is not obvious, but is sensible. And so you can project the Stokes line into real space and predict that across this Stokes line, which is the same Stokes line that you derived, there are real waves that switch on, which makes sense, right? And one could perform, if you had the skill, one could perform a numerical experiment where you're resolving this to smaller and smaller values of epsilon. And the key is that if you were to resolve it to sufficiently small epsilon, you look at just the right location in the flow field, you will hopefully see the wave switching on. Moreover, if you had infinite computational power and you can look even further, you can even predict that the Stokes line has some finite width which scales with epsilon. That's the Stokes line smoothing procedure that Chapman demonstrated earlier. So you could try to do that experiment, but it's actually pretty hard. The second comment I'll make is the question of smooth bodies, right? So you present this theory to an engineer and they say, well, that's all fine and good. What can you tell me about actual smooth bodies? And this presents a very interesting problem that I think has kind of fundamental implications for some of these methodologies. So in terms of the question of how to approach smooth problems, there's kind of multiple answers I can give about that. The first answer is a bit of a flippant answer. So I look at this configuration, and this is for flow over a rigid step. Now I know that I can look at any interior streamline of the flow, so any of this light gray lines, and I can imagine that that streamline, because there's no flow that passes that streamline, I can imagine that streamline is itself the boundary of your domain, of your flow. And the solution that you've predicted has to be the same, it must be. And so therefore, this solution that you see here must be the free surface waves that corresponds to flow over a C infinity boundary, a smooth boundary that corresponds to one of these gray lines. It's a bit of a flippant answer, right? Because it doesn't tell you the actual inverse problem, which is what you're actually wondering about, which is if I were to draw you, if I were to give you a function, an arbitrary function, can you tell me that corresponds to the boundary? I draw you an arbitrary shape. Can you tell me what the free surface waves are? So it tells you the theory is not limited by the fact that your boundary has to be piecewise continuous. It'll work for smooth bodies, but it doesn't tell you much more than that. And I'll leave you with one final point about this, which is that analytic continuation is ill-posed, right? So here we took a solution along the free surface that corresponds, in this case, to a step, and we said, let's analytically continue this. Now, if you gave me one of the streamlines for the flow, I would tell you that the waves are predicted by a singularity that corresponds to a step that you didn't know existed, right? But I can also perturb that boundary by a very small amount. And because analytic continuation is ill-posed, you know that can introduce arbitrary singularities in the complex plane. So what does it mean when your exponential asymptotics is so highly contingent upon the distribution of singularities in the complex plane, and that's an ill-posed procedure to analytically continue in that manner? So that has some, I think, some important implications when you're trying to study flows through smooth bodies, and that's something that we're looking into at the moment. You can also make this problem a little bit more difficult. You can add surface tension into this problem. So now instead of Bernoulli's equation with just this first term involving the Froude number, I can add surface tension into the mix. And in doing so, basically I can introduce a whole range of additional effects, which now I have Stokes lines that may correspond primarily to gravity waves. I have Stokes lines that correspond to capillary waves. I can actually have interactions between the two. I can have intersecting Stokes lines. This is a complicated problem that we still don't fully understand, but it kind of shows you how this analysis can be upscaled and to develop some really interesting and intricate mathematics. Another note is I can do this without boundaries, right? So this here, I'm going to play this animation. This is what's known as the classic Stokes wave. So this is a wave that is traveling with constant shape towards the right, perhaps the most famous nonlinear water wave. Now we know that if you observe these kinds of waves in nature, that you can you have the picture towards the right, that near the crest of these waves, you can have little parasitic capillary ripples due to the influence of surface tension. And in '63 or thereabouts, Lonke-Higgins proposed that actually you can try to capture these parasitic capillary ripples using series expansions in the Bond number. So the kind of these classic initial attempts at trying to capture exponential asymptotics. So this is something that you can do. You can show that in fact there's a Stokes line that comes from a singularity above the crest of the wave that impacts the water, and that is the switching on of your little capillary ripples. And what's interesting about this problem, what makes it difficult, is that the Q naught and the theta naught that are involved at leading order must be determined completely numerically. So this relates a little bit in part. A few days ago, there was a lecture by Gerald Dunn where he talked about the need to develop schemes to find singularities in complex plane by Pade approximates and that sort of thing. So this is something of the same sort, where in order to do the analysis, the exponential asymptotics, you have to know something about the singularities, but you only have numerical solution along the axis. So you need to continue off the axis, find those numerical solutions, and go through with your scheme. Okay, so I've got a couple minutes left, or 2-3 minutes left. So in the last few minutes, I'm just going to touch upon one of the applications that John Chapman mentioned in his public lecture. in the public lecture last week. And the application, this is another classic problem. This is nothing new. This is a classic problem, another classic problem along the same lines as the Kruskal-Seeger crystal growth problem that kind of launched this area of exponential asymptotics and applications. So this is the 1958 experiment by Safnan and Taylor. You have a Healy-Shaw cell, which corresponds to two very closely spaced pieces of plexiglass, and you put a viscous fluid on the interior and you pump air from the top. And what happens is that the interface, the air-fluid interface goes unstable, and you have the development of these fingers that form. And Safnan and Taylor had the following thought. They said, well, let's assume that we can write down a toy model where each of the fingers is just simply propagating, and the adjacent streamlines, which you see here in red, you can think of it as a channel. So essentially, you think of a model where you have a single finger propagating in the channel. And the relevant non-dimensional parameter that comes up is this lambda parameter. This lambda parameter, which characterizes the relative size of the finger width here, marked in orange, with the spacing between the two red lines. And this is another problem. So earlier we talked about waterways. When you work with Healy-Shaw flows, flows in this configuration, that is also a potential flow problem. So you can also write down a boundary integral formulation, also involving a q and a theta, the speed of your interface, the angle of your interface is theta. And it involves this parameter of the finger width, this lambda, this kind of unknown parameter. And you can develop approximations in the limit that this capillary number tends to 0. So Safnan and Taylor wrote that the most interesting feature of the results exhibited is that in all cases, the value of lambda rapidly decreases as the capillary number increases till it reaches a value which is very close to a half. I think this is a typo, by the way, my typo. I think they meant the inverse capillary number, what they're referring to here. So the point here is that as epsilon tends to 0, right, what they find is that the finger width tends to a half the size of the channel. And they couldn't find a theoretical reason for this. And this is your beyond all orders effects. The basic idea to resolving this is that you have two equations now, your usual boundary equation for Q and for theta, and your Bernoulli equation. The independent variable here is y, where y goes from minus infinity to infinity to correspond to the interface. And you have certain symmetry conditions at the origin, and then a condition that theta flattens out at infinity. As Safnan and Taylor predicted, there is a leading order solution here, which is in fact this experimental picture. The dots are the experiments, and the solid curve is their asymptotic solution. So you see one order asymptotic solution looks fantastic. But the problem is that you have no restriction on lambda. Your asymptotic solution tells you that all possible finger widths are possible, even though you know that's not the case. In this formulation here, the lambda appears in the alpha. And so you can do the Stokes line analysis for this problem, and I leave that. You can look up, there are many, sorry, this is a well-studied problem from the 80s to the 90s. And the punchline is that there are two singularities, one in the upper half plane near where my mouse is, 1.5 here, one in the lower half plane, and those generate sets of Stokes lines. As I continue from the left to the right, I switch on a wave at the first intersection, and what switches on needs to be switched off in order to satisfy that boundary condition, and that is what produces the eigenvalue condition. So this is just a demonstration that the techniques that I demonstrated for you for water waves, you can equally apply those in a very similar spirit to the case of Safnan-Taylor viscous fingering, and they both use this kind of methodology that were introduced in lecture 1. That's it. Thank you very much.
Well, thank you very much for a very nice lecture, especially with the use of all kind of technology. That was pretty impressive. I don't see any questions in the Q&A, but if anyone has any comment, question, remark, let us know.
There is a raised hand, I think.
Sorry, I couldn't see it from here. Where is that? Ah, okay, sorry. I have a question. Yeah, please go ahead if you want to write it, or just admit. Wait.
Can you hear me?
Oh yeah, sorry, I wasn't sure.
Sorry, yes, it's
go ahead here.
Michael Berry. Well, thank you very much, Philippe. That was a really lovely account of all the various subtle effects you can get with these nonlinear waves. But when you showed these parasitic ripples, I noticed, and indeed I'm familiar with them, that the picture you showed, the photograph, shows them only on one side of each thing, whereas the simulation you showed shows them on both sides. Now, you can understand why they occur only on one side from linear theory. It's that the dispersion relation for little ripples on shallow water with surface tension and gravity there's a minimum of group velocity, so that the waves travel faster than the group, and you see them downstream of it rather than upstream as for longer waves. So why don't you see that in your simulations?
That's an excellent question, and I didn't mean to suggest that the problem has been resolved. In fact, the problem is open. So there's I think there's two answers to your question. The first is that in general, viscosity will tend to dampen the waves, and so you're not going to have an infinite train of parasitic ripples. The second is an open question, which is, let me take a steady state or a traveling wave approximation of the potential flow problem with gravity and capillary in there. Do there exist asymmetric solutions of that problem? Or do there exist, so there certainly exist symmetric solutions, which are the ones I showed you. The asymmetric solutions, I don't think, so this relates to current work. I think we've shown that asymmetric solutions will not exist in those problems, which suggests that perhaps the formulation is wrong. And what you need is a quasi-static formulation where the ripples are allowed to propagate on the solution of a steadily traveling gravity wave. But it's a very interesting question. And all I can say is that no one has given a very good answer to that problem. My feeling is that the steady formulation is incorrect, and you need a time-dependent formulation. You need to do your exponential asymptotics in a time-dependent formulation, allowing little ripples to propagate on the surface of the gravity.
Well, that's very interesting, because when you see, after the rain, water running down a sloping street, for example, then you can often see trains where there are quite a number of these maxima, each of which has ahead of it some ripples. And it seems to be a fairly static pattern moving downstream. Of course, as you say, viscosity suppresses. There's only a finite number, but you do see them very clear. Okay, now will you allow me to make another more general comment? You see, there is a situation easily observed where you don't have any steps on the bottom, but still you can have a step on the top. And I'm referring to tidal bores. There's one near Bristol, which is world famous, and you can just literally see this pattern. And for many years, I've observed this, and I wanted to understand the shape. There's a very characteristic shape of undulations behind this moving front. And a couple of years ago, I did make a theory, and I wrote about it. And the interesting thing is that you can understand all the qualitative features with a linear theory. I mean, it turns out to be some linearization of KdV, but it's an unusual situation where the tide is coming in with one speed, and it meets the river flowing downstream with a different speed. Now, you can superpose ordinary linear waves given by the dispersion relation, but the superposition has to take into account the fact that at large distances behind and in front, you've got different depths. It brings a pole into the superposition. And then it turns out you need to use uniform asymptotics of the integral, and that's where the connection comes with this program. It turns out that after it's propagated for a long distance, which it does, I mean, many kilometers is a relevant parameter, which is several thousand when you see this bore. Whatever the initial shape, the emergent shape is the integral of an Airy function. Now, of course, the Airy function has in it all the oscillations on one side, but not on the other. So that's where the theme of this school comes in. And it turns out that this moving front is very closely analogous to horizons in relativity. You can have waves on one side, but not on the other. And it depends on whether the speed of the waves is greater or less than the speed of the water, and that is different downstream and upstream. So you can develop the theory linearly, quite accurately, and it doesn't involve all the subtleties that you've described, but it involves still the area function, which we know contains this sort of primordial Stokes structure. Just a comment.
Thank you. That means is very interesting. I should look into. I've known about some of that work, but one comment I'll mention is there is a connection between what you've said and some of the pictures I've presented.
Yes, indeed.
That when you study waves over a step, the traditional linearized theory assumes it's a single dispersion relation that relates the flow upstream and downstream.
Yes.
But when you try to do this kind of exponential asymptotics, it tells you that there is two different dispersion relations because the size of the step can be quite large. And so that's kind of, I'm curious whether there are links between what you've said about the undulating bores and these configurations.
Yes, well, exactly, because the dispersion relation involves the depth, and that varies. It's different on one side from the other. So that's all part of the story. And see, what frustrated me was that for years I've seen papers about tidal bores, and they're all nonlinear. And so you can do numerical calculations or whatever, but it's much simpler. You see it linear, and the slopes of these bores are very gentle. They're not sort of sharp fronts move. I mean, occasionally they are, mostly they're not. And they're just a few degrees, 10 or 12 degrees is the slope. So linear theory is reasonable, and it gives you a nice analytical formula from which you can get a large number of conclusions and predictions. That's it. Anyway, but thank you for your talk.
Thank you.
Thank you.
Yeah, sorry to interrupt. Maybe we should continue because we are running a bit over time. So there will be more time for discussion later on. So thank you very much again for the lecture, and I think we move to the next one.
Hello?
Oh, hello.
Yeah, I'm here.
Yeah, so can you try to share a screen
Yes.
or please?
Screen.
Okay, this is working fine.
Okay, so is it working?
Yeah, so please go ahead.
Okay. Can you see my cursor? Sometimes there's a.
Yeah, I think it's fine.
Oh,
Here,
okay,
please.
great. Oh, hold on one sec. There's. Okay. All right. Well, first of all, thank you, Philippe. I really enjoyed the talk. This was very interesting. And so I will continue from where I left off yesterday. But before I do, let me give a quick recap of yesterday's lecture, and then I will move on. Okay, for each WKB problem, we can draw a Stokes graph like this, where each of these dots are turning points associated with the potential. There might be multiple turning points and so on and so forth. I will. I also discussed that at each Stokes region, where if I can resolve the turning point to a simple turning point, ARAW type, it locally looks like this. There are three Stokes lines emerging from the turning point and then a branch cut. And I also discussed the Stokes phenomena around each ARAW type turning point, right? And we saw that in each Stokes region, separated by Stokes lines like this, locally we have a Borel summable resurgent expression given as a linear combination of two resurgent wave functions that are functions of x, and two constants which are also resurgent functions of h bar and so on, but they don't depend on x. Okay, and then around each ARIA type simple turning point, I worked out the Stokes jumps that these coefficients see. And when normalize if we normalize the wave function appropriately, namely at given turning point, these coefficients take this simple form. There's no h bar dependence and so on. Okay. And I also showed that these are consistent in the sense that when I make a full loop, I indeed obtain one, the unit matrix. So it's a trivial monodromy. Okay, and now our goal is to take such local solutions and glue them together and with multiple turning points. Okay, so a little more formally, we can view this problem. This is the language that Delaware, Dillinger, and Pham use, and following Ekai's work. So we can formally or algebraically view these local solutions in a given Stokes region. So we can view these constants, resurgent functions, the C plus and C minus, forming a ring. And our solutions locally are can be considered as a module, a rank 2 module, because we have two generated over this ring. And each Stokes region, we have a different ring and a different module, and the relevant Stokes phenomena are isomorphisms between these modules. And we want to construct such a algebraic structure that relates all these local solutions around each. So now let me begin with the simplest case where we have two turning points. Okay? So as I said, the local Stokes jumps take a simple form if I normalize my wave function in such a way around the turning point where I integrate from the emerging from the given turning point. Okay, those matrices that I show are implicitly assume that type of normalization. Okay? Now, if I go to a different turning point, now I normalize in a different way because now my normalization is determined at this other turning point, x1. So I will denote these wave functions with different normalizations explicitly here. Sometimes as a superscript or sometimes as a subscript, but sort of x1 and x2 or whatever turning point in parentheses just mean that that's associated with that normalization. And when I use it for the constants, they refer to the constants assuming this type of normalization. Of course, I'm free to normalize in whichever way I want, and these two different normalizations are actually related to each other, right? So when I instead, if I choose to normalize at x1 instead of x2, then these constants are going to reshuffle and will be related in the following way, right? Because if I, for instance, change my normalization from x2 to x1, I just need to multiply psi plus and psi minus with this factor. Which means that these constants corresponding to different normalizations are related with through this diagonal matrix. Okay? Now this is going to be important because I want to patch what happens at this turning point and what happens at this turning point. And if I want to use those simple matrices, I want to, change my normalization. And when I do that, I will pick up these factors of that are given here. Okay, so actually these factors have a very nice interpretation. So they are integrals between these two turning points, right? So it is the integral of my action. It is the action identified with an integral between these two turning points, and this is my cycle, one of my cycles, right? So for each turning point, this matrix can be written as just this matrix depends on h bar and of course the energy, and that function is nothing but my quantum action. And the exponential of that, and it has a name. It's called the Voros symbol, of course, named after the seminal work of Andrei Voros. And and there's a power of 1/2 here because the cycle is defined as a full. It's the integral, the S gamma is defined as an integral over the full cycle, whereas going from just here to here takes the half of that cycle. So that's why there's a power of 1/2 here. Okay? So this gives a simple connection formula going from this normalization to that normalization. Now what I have to do is to put together these Stokes jumps that I discussed yesterday with this connection relation that relates to two different normalizations. Okay, let me work out an example to make this clear. It turns out actually there is a rather famous example in physics which has such a Stokes graph. It's called the harmonic oscillator. Okay? The harmonic oscillator, it's one of the perhaps the most studied examples in quantum mechanics. It's the potential is just a quadratic function, and we have two turning points that are symmetric, that occur at square root of 2e and minus square root of 2e. Right? Now I want to impose a condition on my wave function that that on the real axis, I want a normalizable wave function. So I want my wave function to decay when I go to the right in real axis, and again to exponentially decay when I go to the left. So this condition makes sense if I'm considering a physical system, but in general, if maybe not for the harmonic oscillator, but in general for different potentials and so on, if I'm studying a different problem, I might want to impose a different condition on my wave function, which actually happens in certain examples. I can repeat basically the same steps to obtain the results for different conditions that I might impose. Okay, but this is the condition that I'm going to impose. So, so now here in region A, I have so one of the coefficients is 0. C plus is 0, so that I have an exponentially. So because the plus is exponentially growing, exponentially decaying function, and here C minus is 0. Okay, because psi minus is exponentially growing, psi plus is exponentially decaying. And the Stokes jumps relate these coefficients in different regions. If I start from here and analytically continue there, or vice versa. Even if I start with a form like this, I might actually generate an exponentially growing piece if I analytically continue, let's say, from here to here. So so that I want to make sure that that doesn't happen. And we will see that that condition can only be satisfied for certain values of the energy, and that would be my exact quantization. Okay, so we can work out these Stokes jumps. As I said, going from so here I have an Airy type Stokes algebra, if you wish. So if I go in particular, let's start from here. If I jump this line, I will pick out a factor of 1i01 type matrix. And then I'm here in this section. Now, in order to use the Stokes matrices that I derive for the Airy function, I have to change my normalization now because I want to execute my Stokes automorphisms for this Airy graph. Then I insert the connection matrix that changes my normalization from x2 to x1, then I can continue going from jumping this line. And then in order to compare the wave functions, I change back the normalization to x2 so that I have a relation between the coefficients that I obtain if I analytically continue here. Okay. Then initially I start with the condition that my C plus was 0 because I want an exponentially decaying function here. But again, if I do this analytical continuation and so on, I see that even if I turn it off here, I actually turn it on by this analytical continuation process. And it does generate for me a C plus term here. And that cannot happen because I want a square integrable wave function, I want an exponentially decaying wave function, and so on. Which means that the coefficient, this coefficient has to be 0 so that I have a nice wave function. And that condition is basically 1 plus the Voronoi symbol associated with this cycle is 0. So this is an example of a connection formula, and this is called the Voronoi-Silverstone connection formula. And basically, this is the prototype of the exact quantization procedure that also applies to other potentials and so on. Not just okay. Sorry. Yeah. So this was the work by Voronoi and Silverstone. Actually, if you just as a historical remark, if you look at the paper by Silverstone, it's very sharply worded. It starts with the sentence that goes something like the standard treatment of the JWKB expansion is incorrect, and then explains how to correctly do it. I actually recommend reading that paper. Very, very sharp. Anyway, so now we can also cross-check, just like I did in the Airy function case, what happens if I go just a full circle around around the Stokes graph. And so if I do that exercise, you can show that if I go for with a full circle, I pick up a factor like this here. And in order for my wave function to be single valued, again, there's a minus sign here, and then there's v and 1 over v. And minus v has to be equal to 1, so that this is an identity matrix, which means v V has to be equal to -1, which is the same as V plus 1 is equal to 0, the condition that I derived earlier. Now, this is the exact quantization condition because this is a function of energy. So not all E and H bar, actually. So not all values of energy satisfies this relation. Okay. So earlier, when I gave a sort of an outlook, an overview, I said there are two parts, loosely speaking, of the exact WKB problem. One of them is to work out the Stokes isomorphisms, and the other one is to find the exact quantization condition. This is the exact quantization condition. And what's nice about it is that it's a function that, I mean, it might still be a complicated function of E, but it is a fairly simple function of the Borot symbol. So the utility of using this the Borot symbols is that the exact quantization condition in terms of these functions is actually typically not that complicated. Of course, then extracting the energy levels and so on from that might be a different problem. And I will tell more about this, but Borot symbol itself also is a resurgent function of H bar. So all the resurgent analysis that we talked about apply to the Borot symbol as well, and solving this equation that applies to a resurgent function also gives me the energy level, the allowed energy level is a function of H bar and perhaps some other parameters that are shown here as a function, as a resurgent function as well. So the solution of this equation, or the inversion, gives E as a resurgent function of it. Of course, it's not simple as for the wave function. It's the Schrodinger equation. It's a linear differential equation. For E, it's a more complicated equation, but still, and we will see that because of that, the resurgent expansion for E is more complicated. Okay, let me move on. So in the case of harmonic oscillator, the action actually is linear in E. So it's 2 pi I times the energy level. And I stress here that, so on the left-hand side, you see I then put the 0 index that denotes the order in expansion in H bar. But on the right-hand side, I just have the 0th order term. I don't have the corrections here, H bar corrections here. It turns out, this is not a typo. For the harmonic oscillator, the contribution of all the other higher order column actions evaluated, between these two turning points, they all vanish. They're all 0. So so this is an exercise actually that you can do to verify that higher order actions for the harmonic oscillator actually do not contribute to this. One way to see that is if you write down the higher order actions, and because we know the integrand, and the higher order actions are generated by so this is my square root of 2 here. And if you do the Riccati, if you apply the Riccati recursion relations, you can generate these higher order terms, and integrated between these two turning points, you can actually show that as functions of E, they can be expressed as just derivatives, some combination of the lowest order action and some derivatives of E applying to it. And because the leading order term is linear in E, all those derivatives, the higher order derivatives acting on the lowest order action here will give you 0. Okay, so that's sort of a strategy that you can follow. There are other ways to show that, of course. Okay, so moving on. So then this equation can be easily solved. So I have on the exponent 2 pi I times e divided by h bar. This has to be equal to -1, which gives me the e as h bar times an integer, because this solution has this equation has infinitely many solutions, which are labeled by an integer n, and plus a half because there's a minus sign here. But this is the quantization condition, right? So instead of all, just a continuous spectrum of energy levels, I only have a discrete set. I could also so if for instance, if I typically this is the interpretation in terms of quantum mechanics, but if you view this as a relation between E and H bar, so this just tells you, I can also invert this relation and say for I'm allowed to have any E, but my H bar is quantized, if that is more appropriate for the problem that I'm interested in. Okay, so in certain cases that's the interpretation. All right. So let me actually illustrate this in sort of graphically. The solutions to the Schrödinger equation for the harmonic oscillator, which is also known as the Weber equation, are known. They're called parabolic cylinder functions. In actually the digital library in NIST, it uses a different convention, but I'll use this one. And two independent solutions are d of x and d of minus x here. All right, and nu is my index here, and it doesn't have to be an integer. So the parabolic cylinder functions are defined for any value of nu. And nu is identified as E over H bar minus 1/2 if I massage my Schrödinger equation to put it in this form. And the exact quantization condition tells me that nu has to be an integer. Okay, so what happens if nu is not an integer? So for instance, I plot here the wave function for the fourth right? So as I demanded, it's exponentially decaying in both ends here. If this condition was not satisfied, I can't fulfill that condition. For instance, if I change nu a little bit, my wave function diverges here. If I change nu on the other hand, it still diverges here. And if I can scan any non-integer, so if I just scan these the behavior of these parabolic cylinder functions, I will see that it only has this nice civilized form only for integer nu, and any other nu it will diverge, and my normalization will not be satisfied. Okay. Now this also has a nice interpretation. So the condition, the exact quantization condition that I derived from the harmonic oscillator just tells me that my action around between the turning points were in the sort of allowed region. So when E is less than my B minus E is negative, so that my particle is doing the nice classical oscillations. So that's the phase space volume. The S computes the phase space volume, and the condition was that it's 2 pi I times h bar times some integer. Well, this is the Bohr-Sommerfeld quantization condition, right? So the classic the volume in phase space is quantized in units of h, which is 2 pi h bar, and this I is, remember, I define my action and my momentum with a relative sign of I compared to the physics convention. So this is the good old Bohr-Sommerfeld quantization condition, right? Now, I can make a conjecture that says, well, if I consider all orders in WKB expansion, if I consider the corrections, the H-bar corrections to this classical action, then maybe that's quantized in a way that, you know, I just replace here my classical phase space volume with the quantum action. And this is actually what Dunham proposed. And if you read, there's a section in Dunham's paper that says, and he also realized that you can do this and you can solve for E. Sorry, there's a factor. There must be a factor of H bar here. But anyway, so it says in his paper that due to its asymptotic character, the series is diverges for actual finite values of B. So B is his H bar. What he calls B is H bar. And it can therefore used to find energy levels only to a limited degree of approximation because it's an asymptotic series. This, I think, he's talking about optimal truncation. Like that. The quality of the approximation is in general better for systems which are nearly classical, H bar is small. For those showing large quantum effects, this is not surprising since the first term of the energy level equation gives the classical Bohr theory. So he realized that if you can do this and you get an asymptotic series, and he basically stops there. Okay, and of course now we know, equipped with all this resurgent analysis, we know that this can't be the full story. As soon as you have an asymptotic series, you should be thinking about exponentially suppressed terms and resurgent symbols and so on and so forth. And this is indeed the case. So this quantization condition is not quite complete. Okay, what it leaves out is actually it's kind of obvious here. I didn't have a subscript here. You generally have other cycles, right? That enters into the problem. For instance, for my double well, I have another cycle here that goes underneath the barrier, right? Gamma 2. So, well, then you can say, well, okay, it's the classical one, or the action corresponding to the allowed region is quantized and so on, but then you're forgetting this part. Okay, so actually, what you're leaving out exactly are the non-perturbative parts of the resurgent expansion that are associated with this gamma 2. Okay, these will generate e to the minus some constant over H bar terms, and they do show up in the energy spectrum. Okay, and physically they're associated with tunneling between these two minima. Okay, and even physically, I know that I need to take into account tunneling, which means that somehow this other action has to show up in my exact quantization formula. Well, actually, this is not quite correct. This C has to be 1/2 of this one, and I'll show that 1/2 is important. I'll show why. So in general, then instead of, again, talking about actions, we can talk about Warrow symbols. So in the overview is that in general there are multiple cycles, and associated with each cycle there's a Warrow symbol, and it's also important to note that these Warrow symbols take value in the first homology group of the spectral curve. Okay, so you can think of them as functions of equivalence class of cycles. Okay, there are functions of H bar. They exhibit Stokes phenomena, and what we will see in a bit is that the Stokes phenomena in H bar, when I move around, relates actually different Warrow symbols. So it reshuffles different Warrow symbols, but it's a it's an automorphism, so it takes a combination of Borel symbols to another combination of Borel symbols. So, so the whole exact WKB problem can be reduced into finding these relations between Borel symbols as I go around my Stokes graph. And again, I have to impose certain conditions on my wave functions, boundary conditions, normalization condition, and so on and so forth. And that condition will give me some further relationship between these Borel symbols, and that will be my exact quantization formula. And it's not just the action associated with the classically allowed motion. It will be all in general, all the cycles that appear in my spectrum. Okay, that's my overview. So now, as I said, the Borel symbols are resurgent functions, and they're not Borel symbol if there's a singularity in the path of the Borel integral associated with my Borel symbol. And this actually happens when two cycles intersect between each other. And we can actually resolve this by turning on some imaginary part of H bar, or if this happens for complex H bar, sort of deforming a little bit the rotating a little bit H bar in the complex plane. And by doing so, I introduce these lateral Borel summations, and they give different results. And the difference is encoded in the Stokes automorphism. And basically, these jumps in Stokes jumps in my Borel symbols can be packaged in terms of the what the Stokes automorphism does to each cycle, okay, around a Stokes line. All right. So now again, let me illustrate these in my example, the double while example, because, well, I can't do this in harmonic oscillator because there's only one cycle, but double while is the next example where I have actually two cycles, gamma 1 and gamma 2. And this is a symmetric double while, so these two whiles are symmetric. Therefore, even though it looks like I have three cycles, this cycle gamma 3 is actually the inverse of the my first cycle. So they're actually identical with a minus sign. So I have gamma 1 and gamma 2. And again, our spectral curve is a torus, and these two cycles are associated with two independent cycles of our curves. Okay. Now, recall the Stokes graph of my double while. These two turning points are connected by the Stokes line. So it's not the case for here. These two are not connected by a Stokes line, but these two turning points are connected by a Stokes line. And you see there are, and remember that these Stokes lines sort of are left-hand symbols where the imaginary part of the action is conserved. So if I have a Stokes line that connects two turning points, then in Borel plane, there will be singularities along each other's axis of Borel integration. And now I have to deal with this situation. So I called it singular Stokes line. I think there are some sources that call this, when this happens, it's a singular Stokes line. The Delbert, Dillinger, and Pham calls this a critical Stokes line, but basically it's a Stokes line that connects two turning points, and it will lead to a singularity in the Borel plane. Okay, we can resolve this ambiguity by giving a small imaginary part to H bar, and indeed, if I do that, you see this line that separates So that connects the two turning points split, but it splits in different ways. If argument of h bar is negative or argument of h bar is positive, if the geometry is different. But in each case, it's Borel solvable. So let me start with argument of h bar is positive. Now I demand two things. I demand again that my wave function is nice and civilized in this region, so it exponentially decays. It's normalizable in region A. And the other condition that I will demand is parity. So either the wave function vanishes, or the derivative of the wave function vanishes at 0. And here x equals 0 is right in the center here. Okay. I can express my boundary condition this way, where eta is a number that's either 1 or -1. So eta 1 corresponds to parity even, and eta -1 corresponds to parity odd. Wave function. So these are two separate wave functions. Now, again, I can play this game and follow the jumps and the coefficients and so on, and put in the Voros symbols that connect this cycle to that cycle, and this turning point to that turning point. So because I have two, I have to take into account two different Voros symbols when I play this game of Stokes automorphisms. But similar to the harmonic oscillator case, I have a connection formula that looks like this. There's an -1. That's just conventional. When I, there's the orientation of my cycle basically, and then there's a 1/2 here, which is going to be important, and my parity shows up here. Okay, again, I can play the same game, but when argument of h bar is negative, then I get another connection formula, which is different than this one. You see that this sign is different, and the power is different. Okay. Yeah. So compare these two. So I will, the second Voros symbol v of gamma 2 doesn't change, right? So so in order to distinguish between these two cases, I will use this plus and minus notation here, the corresponding to the argument of h bar. All right. Now I massage it a little bit. I take the square and so on of the connection formula. I can put it in this form, and now you can see, you just comparing these two formulas, you can see that the Voros symbol on the left-hand side and right-hand side are related in this way. Okay, the Voros symbol here is equal to Voros symbol here in this region with some factor that depends only on the second Voros symbol, and the second Voros symbol doesn't change. Okay, it sort of is similar. You see in the Stokes jumps, the exponentially large one acquires a Stokes jump, an exponentially small one doesn't, and we will see that this is exactly the case. Oh, this basically says that the Stokes automorphism is given this way, and for the other Voros symbol, it doesn't change anywhere. Okay, so this relationship determines all the information about all the Stokes jump about in my exact WKB problem. This is called the Delibert-Dillinger-Fan formula. Okay. There is a very nice geometric interpretation of this formula, where this power -1 here, actually the intersection number between these cycles. Okay, I have gamma 1 and I have gamma 2 here. This is sort of faded because it's on the other sheet. So gamma 2 intersects with gamma 1 here, but it doesn't intersect here because it's on the other sheet. That's why it's sort of faded. That's what happens when you cross the Riemann sheet, you fade away, right? Okay. So it also intersects gamma 3, but gamma 3 is actually identified with minus gamma 1, so there's only sort of one such intersection. But if I was considering an asymmetric double well, then I will also have V of gamma 3 here, which will obey a similar formula, but with the opposite sign because the orientations here and here are different. But this is the interpretation. Okay. Now, in general, this is also true. In general, I will have many minima and maxima and so on, and different cycles, and it could be the case that a cycle like this might intersect several other cycles. I didn't plot it here this way, but in general it could happen. And the general formula is that the Stokes automorphism for a given cycle I is a product of this form where it contains all the other cycles that intersect with gamma I. Okay. There's a recent paper by these folks which actually consider explicitly work out this example in sort of more complicated potentials with different numbers of minima and so on. And I recommend you looking at it. Okay. Now let me. This was the first part of my WKB problem, to work out the Stokes automorphisms. Now the second part is the exact quantization condition. Okay, and I already derived it. It's this one here. But now let's compare these. Have a closer look at these terms. Okay. So V of gamma 1 is the cycle associated with the classically allowed region here. And in my choice of normalization, it's pure imaginary because again, you see my Q is V minus E, okay? But now, I keep changing my notation. This S hat is what I call SPT from now on. I forgot to change this one. This is SPT, okay? So what I do is I just factored out factored out an I. So this is what I call SPT. I just switched the relative sign so that SPT is real. Okay, so it's the classical action plus quantum correction. So this is e to the I over h bar times SPT. Sorry about that. I'll fix it before I send my slides. Okay. Whereas the other one is dear God, this is real. It's not pure imaginary. Okay, so this is real because again, with my choice of normalization, V is always greater here than E. Then this is real. So it's exponentially suppressed compared to V1. So this is why this is one of the reasons why V1 encounters a Stokes jump and V2 doesn't, because it's exponentially small compared to the other. Okay. And I have a factor of 1/2 here, which picks out half of this action. I will call this an instanton action, or this is associated with tunneling. Okay, and this half will be important, but you can view this as the instanton action and quantum corrections. All right, very well. So let's work out the exact quantization condition in a little bit more detail. So if we neglect, so you see this is exponentially small compared to this one. So let's just neglect the exponentially small part. Well, I have this is what I have. This is nothing but the Bohr-Sommerfeld quantization that Dunham was talking about. And I can indeed evaluate this action and invert this to get E as a function of the level number and h bar and so on. In contrast with the harmonic oscillator, the higher order actions are not 0 in this case, so they do contribute. So what I have is a formal power series in h bar that also depends on my level number. Okay. Of course, at this point, I don't think you would be surprised to hear that this is an asymptotic series. Okay, it diverges and so on and so forth. One thing, oh yeah, so I made this expansion at the bottom of the well so that, I have, at the bottom of the well, the motion is harmonic, so I have a harmonic oscillator plus corrections, but in general, I can expand in different values of E as well. But this is the most sort of straightforward thing to do at this point. Make connection with the harmonic oscillator. And notice that there's no dependence on eta, the parity, and it just tells me that perturbative spectrum is doubly degenerate. For every odd parity even state, there's also a parity odd state which has the same energy, according to perturbation theory. I call this perturbative because this is what I would get if I calculated perturbative corrections to the harmonic oscillator problem, as I said. Okay, that's the terminology. Now, let's work this out in slightly more detail. So I have my zeroth order classical action, the second order action. You can derive these fairly easily. But what you would notice is that these integrands are slightly different than what I had in the first lecture that you get from solving the Riccati equation order by order. And the reason is that because this is a closed integral over two turning points, so some of the terms can here be eliminated, which some of those terms which are total derivatives in x can be eliminated. So I can manipulate those expressions that I get from Riccati to make them look like these ones. Okay, so that's an exercise that you can. And the zeroth order action is a hypergeometric function that looks like this. And all the higher order actions can also be computed. And there are actually some hypergeometric functions which can be packaged in the following way. They're linear combinations of the classical action in its first derivative multiplied with some rational functions of E. Okay, tomorrow I will discuss why this is the case, but just keep, just believe me for a second. So you can generate all these things and so on. So I can expand around E equals 0 and just invert the series. For example, if I expand this this term, it's 2 pi E plus E squared and so on, and I can do the same thing for h bar squared, h bar to the 4, and so on and so forth. You see, for instance, just taking this term will give me the harmonic oscillator, and then the other terms will generate these coefficients and so on. This is fairly straightforward. Okay.
Sorry to interrupt. You have like a couple of minutes left.
Yeah. So I have. I'm at minutes 50 in my timer. I'll be done in like 5 minutes.
Okay, no problem.
Yeah. Okay. So now I can take into account the non-perturbative corrections by taking into account this term here. Yeah. Now, again, let me start from E equals 0 and just make an ansatz, like so that my energy is the harmonic oscillator spectrum, n plus a half. But a little bit, so it's not exactly an integer, but an integer plus a little bit, and then I can plug it here for v of v gamma 1 and expand in epsilon, and I find that the leading order epsilon, that bit, is indeed exponentially suppressed, and this factor s inst is actually the leading order term in this instanton action, which is 2/3. Okay, and then I can obtain the first order exponentially suppressed corrections. And you see, there's eta here. There's plus minus sign. So this does depend on the parity. And in fact, the physical spectrum of the level well is not degenerate. There's level splitting between odd and even levels. And if I did just pure Bohr-Sommerfeld, I would totally miss this, because the level splitting, the leading term in level splitting is exponentially suppressed compared to the level itself. Okay, so this is not only a quantitative correction to the spectrum, this is also a qualitative feature of the spectrum, the resurgent terms. I can similarly, I can work out the fluctuation instanton fluctuations because they are again given by the same type, the same integrands, just different cycle. Okay, and it's again a hypergeometric function. It's slightly different hypergeometric function, same story, and these correction terms will give me fluctuations around the instantons. And then the exact quantization condition can be put into this form where I have the classical action and some function. Now, let me look at something slightly further, which is that let me look at this fluctuation term more carefully. Okay. So this is again some hypergeometric function that I can expand. Even the zeroth order term gives me this log because it's now I'm expanding around the hypergeometric function around 1. Okay, now which gives me this log term. And when I make my ansatz here and plug it into this expression, my this log term gives me a log of h bar, or more concretely, the fluctuation term will have a power of h bar and plus a half plus this bit, and this bit, if I expand in this this fluctuation term in epsilon, in this bit, it has a coefficient log of h bar. And this only shows up when I take this term and plug it back as a feedback into my exact quantization condition and solve the higher order corrections in this bit epsilon. So it only shows up in the 2 instanton sector. It's doubly exponentially suppressed, so this log. And physically, this has a very nice interpretation, which I will continue tomorrow. Okay, so let me finish here, and I'll take questions if there are any, and I will take it from here tomorrow.
Okay, thank you very much for the lecture. Are there any questions, comments? I can see a comment on the chat from Andre. I think that everybody can see it. If not, please let me know and I can read for you, but I think he sent it to everyone.
Yes. Okay. 43 and this for this, which is clumsy because of the higher order corrections to be treated separately, being non-integrable at the turning points. I see. Yes, I see. Okay. This discussion is mostly from Andre's book. So yeah, I use the same normalization as it, but yeah, I agree that I think there were a couple of sources who normalize it at infinity, but yeah, I agree.
Okay, are there any further questions? Quick questions before we move on? Just double check the Q&A. I don't see any other questions. Well, if not, again, there will be time later on.
Yeah, I'll be around for the tutorial.
No problem. So thank you very much for the lecture, and then we'll have the last part tomorrow.
Okay.
Yeah. Thank you.
Thank you.
Yeah. Thank you. So is Daniele around? Or
I am.
yeah, okay.
Let me just
Good.
share my screen.
Okay. So yeah, so the last speaker of this session will be Daniele Dorigoni with the second part of his talk. He started yesterday on Eckhouse theory of resurgence. Hopefully that, yeah.
Thank you, Alfredo.
It works.
Perfect.
Yeah.
Should be working. Let me do the layout as yesterday. Sounds good.
So
excellent.
Thank you.
Perfect. Good. So let me remind you briefly what we're discussing yesterday. So we were playing a slightly different game. We were starting with these formal objects, which were formal power series in some large coupling constant. And these were the objects we were calling tilde. And then we constructed this linear operator that takes them and produces convergent functions around the origin. And these were called in them the Borel transforms. And then we wanted to understand a little better the procedure of this resummation. So we saw that if we were integrating along our favorite complex direction, the Borel transform, we were obtaining a possible analytic continuation. So we wanted to understand a little bit more, well, we wanted to put in a certain sense some restrictions on the class of functions that we would like to study. Of course, like in a physical problem, there is no restriction, but we can find an interesting class of functions by putting these restrictions. And some of the restrictions that I told you about were, let's say, few singularities, which meant that I can almost always do this integral along my favorite direction. Maybe I cannot choose my favorite direction, but I can move slightly away from there. And this was this endless continuability. And then I also wanted to put some condition, which is not really super important, but it was just to simplify the story, on simple type of singularities. And we saw that with this condition, where's my equation? Perfect. The type of singularities for the Borel transform were poles and log branch cuts. Plus some regular part as t tends to omega. Good. So in a generic physical problem, the set of singularities that are going to appear is going to be problem dependent. So for each problem we want to solve, and we've seen many, many examples, there's going to be a bunch of possibly infinite number of discrete singularities. So let's put the set of singularities for the given physical problem. Let me say, well, as we said, it's discrete, but possibly infinite, okay? And let me call this set gamma. Then what we want to consider, C, perfect. Then we want to consider a Riemann surface associated to this problem. So let me call R the Riemann surface associated to the problem. And if you wish, you can think it as the universal covering of C minus gamma, or without being that sophisticated, you can simply think of it as paths in C avoiding, oh, what happened? Can you still see my screen? No, you cannot.
No, we see some kind of error message. It was, I
I'm
think it was
sharing
frozen.
it again.
It was frozen for a bit. Ah, yeah.
Perfect.
Now- okay.
Sorry, it's very likely my internet that is a little bit garbage today. Apologies
No
for
problem.
that. I'm working
think
from
now
home
it's fine.
today, so good. So as I was saying, one way to think about this Riemann surface, you can think it as all the paths living in C, originating from the origin, and avoiding the set of singularities gamma. So let me define with h hat of this Riemann surface R, the space of holomorphic functions on this Riemann surface R, which are endlessly continuable and with singularities on gamma. We would like this to be restricted to being simple singularities, but for the moment, let me just assume that they have singularities on gamma. And this is called the convolutive model of the algebra of resurgence function. And of course, now we know that we can also study the multiplicative model just by taking the inverse Borel transform of this object. This is the multiplicative model. So we just put all of these functions together. One technical point that I mentioned yesterday, and I would like to get rid of that, is that note, we had a product on this algebra. We had the convolution product on this algebra in here. And you would really like to have an identity for this product, a unity. Unfortunately, it doesn't have a unity. So you just add it by hand. And this phi hat of t, you write it, remember, as always, as the Borel transform of some function. And I'm going to write it as some complex number times this unity, which I'm going to be calling delta, plus the bit that we have already seen. What this translates into is the term that we were missing. The asymptotic expansion is going to start with C z to 0 plus the infinite series. So this delta satisfies, as the name suggests, it's the unity for the convolution. And of course, if you remember, this object in here doesn't go well with my definition, right? If you remember, my definition was that to the minus alpha minus 1 is equal to t to the alpha divided by gamma of alpha. And in here, alpha plus 1. Okay. And this guy in here would correspond to alpha equal to minus 1, which of course produces a gamma of 0. So this guy does not exist on its own. So we just give it a name. We say that under Borel transform, it goes into this convolution. So at this point, we can extend it. We can extend the convolution product to delta times C, the constant term, plus the germ of analytic functions around the origin. So the reason why it's useful to introduce this object is because now we can give the following definition for a simple singularity. Let me remind you that the object was this one, a simple singularity. We have a pole plus the minor plus regular terms. Let me not even write them. Then at this point, we can define the singular part at omega of phi has the residue times the convolution delta plus the minor. This object in here belongs to this extended algebra. Delta times a complex number, the residue, plus a germ of analytic functions at the origin, the minor. So we can give at this point a definition of what a simple resurgent function is. A simple resurgent function, we call it psi, of the form C delta plus, how did I call it? Phi hat, which belongs to C delta plus the germ of analytic functions at the origin, such that it has simple singularities on gamma, this set of singularities that was given by our problem. So i.e., for every omega in this set, the singular part of psi is going to be alpha omega delta hat plus the minor at omega. So these objects are going to be playing a key role. As we have seen many examples now, the singularity structure of, in general, this psi hat, we think it as being the Borel transform of our perturbative series. The singularity structure, namely the location of the pole, the residue of the pole, and the logarithmic singularities, will have to do with some non-perturbative physics. Finally, I can mention the following property, the proposition that this is a subalgebra of delta C plus the convolutive algebra. And sometimes it's denoted as res simple. So let me just remind you what the key points are. First thing, not too many singularities. There can be infinitely many, but they are discrete. There is no natural boundary of analyticity. Secondly, the singular behavior, the behavior of our function close to a singularity, is captured by, yet again, another simple resurgent function. And finally, we have nice behavior under some natural properties: convolution, composition, and so on. So just to play with a slightly different example of what we have seen, let me give you this exercise. It should be 6. Yes, it is correct. Let us consider a slight modification of this Euler equation that we have seen over and over. So let me consider the following finite difference equation. Psi of z plus 1 minus 2 plus psi of z equal to minus 1 over z. So if you think that z is much bigger than 1, then you could think that psi of z plus 1 is going to become psi of z plus the derivative with respect to psi of z plus ... So in a certain sense, this problem reduces to the derivative plus 1 minus 2 gives me minus psi of z plus ... equal to minus 1 over z. So you see why I say that is a sort of generalization of Euler's equation. However, this is a finite difference equation. Let me ask you this. Find the unique solution to this problem such that the asymptotic expansion starts with 1 over z when z is much bigger than 1. So we want to find the unique solution such that it goes to 0 at infinity. So in here, remember, we are thinking this as a positive coupling constant, let's say. You can try, so for the students, you can try to play with Mathematica. So Mathematica is an R-solve, which is like a solver for recursion relation. So you can try to use that as well. Secondly, what is the set of singularities gamma in this case? Set of singularities for this problem. And finally, what is the most general solution to the homogeneous problem? And what is the connection between this homogeneous solution, let me call it psi h, so psi h solves psi h z plus 1 minus 2 psi h of z equal to 0. What is the connection between this solution and the set gamma? So if you wish, what is the role of the physical, role of the singularities in this case? Okay. So at this point, we have all our machinery. We want to understand a couple of things now. So we want to understand, in a certain sense, the physical role, although in this case, I'm not talking about any problem in particular. So we want to understand what the repercussions of these singularities is going to be for our resummation. And furthermore, how do we actually resum whenever we have some singular directions? And this brings me to something that, luckily for me, Gotche has already mentioned, what is called the Stokes automorphism.
Sorry to interrupt. Yeah. There's a question on the chat that might be relevant to.
Please let me go on the chat.
It's a question about the normalization of the Borel transform. So it might be easier to deal with that now instead of at the end of
You could, absolutely. Thank you, Andrea, absolutely. So doesn't the normalization makes life unnecessarily complicated? Agreed, for simple exponential function. It is possible to normalize the Borel transform so that b of 1 is equal to 1, and then the minor has a function that really includes the leading term. Absolutely, yeah. So I think I mentioned yesterday in the tutorials, you can of course do different definitions, right? So you could define that this guy goes into this guy, or you could also define it that it goes into this guy. Of course, I give a different name, so I have use of notation. So all of these are slightly equivalent. They correspond to taking derivatives. And of course, whenever you take derivatives, you forget the constant. So of course, with a different normalization, you can include them. This is a good point because I can also mention something else that I wanted to mention. Suppose also that you notice that your coefficient, your perturbative coefficient, are growing factorially times some other number that you might recognize. Let me call it some nice number alpha. Let's say alpha good, and some other less good number. Let's call it beta. Bad. If you know of a way to get rid of this combination, then you can try to define an alternative, a modified Borel transform. To give you an example, suppose that your coefficient were n factorial zeta of n times some other number. Then you can actually define a modified Borel transform by considering not the exponential, because remember, this exponential was useful to remove a pure factorial growth. But you can actually find a different measure that gets rid of this one. And in this case, this measure is 1/sinh square of t to the n. This one, I'm not sure about the normalization. There might be a factor of 4. But this one gets rid of you, not only of the factorial growth, but also of zeta of n. So the good thing of this e to the minus t is that it has all these nice properties that we discussed. These other type of kernels are good for some things, like removing something, but they're bad for other things. But there is not a unique Borel transform. So as Andrea was saying, for this particular case, you could have defined it just slightly different to get rid of this complication. Yes, thank you. Good. So let me erase this part. Good. Yes, as I was saying, we want to study a little bit more the continuation properties across singular directions. And this is going to bring us to the Stokes automorphism and the alien derivative. Alien has Stranger and not has Ridley Scott movie. So we start again with our formal power series, which can contain a constant or a term in this algebra. And the corresponding Borel transform, which has this C delta plus Borel transform. How did I call it? Phi. So we have defined this directional Borel summation to be the constant plus the integral between 0 and infinity, e to the minus z t phi hat of t dt. So to go back to Andrea's question, you could have taken this c, put it in the integral, fiddle around with various powers of z and t, and got a different version. I see a dot, so, oh, perfect. Good. So at this point, what if we have a singularity, so an omega in gamma, such that the argument of omega is exactly this direction that I forgot to put in here, the e to the I theta? Well, we can, as I was saying before, since we don't have an accumulation of singularities, we can slightly deform. So we can do what is called a lateral Borel summation. And as the name suggests, you just do the resummation slightly from above or slightly from below. So let's say this is my singular direction, theta. Here is omega. I have a branch cut from here. And I'm going to be integrating along this direction or along this direction. So we can do s of theta plus minus has the limit for epsilon positive going to 0 of s of theta plus or minus epsilon. So in here, I'm doing theta plus epsilon. And in here, I should have used different colors. So let me use different colors. This is theta plus epsilon. And below, I'm doing theta minus epsilon. Good. So an example of this one is the usual factorial, purely factorial growth without any alternation in sign. This is a solution to the slightly deformed problem, phi prime plus phi equal to 1 over z. And the Borel transform is 1 divided by 1 minus t. So you see, as a physicist, if you think of this z as a positive coupling constant, you are hit directly in the face because the integral you wanted to do, which was the integral along the 0 direction, is not defined. Of course, in this case, you would know perfectly well what to do. This integral, you would have just done some principal values prescription. And in many cases, this gives you the correct answer. So this, in many cases, is related to the median summation. But for the moment, let us not go there. If you take this integral is ill-defined because you have a pole on the contour of integration. However, you can just do plus epsilon, so let me just call it S plus. And you can do the integral from below. Let me call it S minus. And remember what we were saying last time, that whenever you were changing the argument of your integration and you didn't have any singularities in that sector, you were giving an analytic continuation. In this case, that is not true. S plus and S minus, although they have a common domain of analyticity, they differ from one another. S plus minus S minus is a little exercise. I'm not even going to write it down for you as an exercise. This is just a contour integral, and it's going to give you 2 pi I e to the minus z. So you see that we have some new object appearing. We started with formal power series, and e to the minus z is a new beast altogether. When z is large, you don't do anything with e to the minus z. You just keep it like that, and you leave it forever. So this is the simplest example of a Stokes phenomenon in this case. Well, I shouldn't really call it Stokes phenomenon at this stage. If omega is one of your singular direction with, let's give it a name, its argument is theta, we call this direction a Stokes direction. And I can give you the following definition. You can compute the difference between the resummation of the two sides. The Stokes automorphism, and as the name suggests, you see, it is indeed an automorphism. So this is usually denoted with mathfrak S. So it takes one of your simple resurgent functions, and it gives you another simple resurgent function. And it's defined in the following way. The resummation from the plus, it's almost equal to the resummation from the minus. However, you need to modify slightly your function. You need to compose it with this Stokes automorphism. Another way to write it is that you can integrate from below. The only thing they need to do, you need to take the identity, but also subtract the discontinuity in this direction. So if you wish, we can say that the difference in the two resummations is given by the integral from below composed with the discontinuity across this direction in here. So in pictures, it's easier to understand what we're doing. So this is again the t-plane. and this is the direction. Theta. So along theta, I have some singularities. And I want to integrate in this direction in here, s of theta plus. Well, I can write it as the integral below the cut plus this other contour. So this is s of theta plus, this is s of theta minus. And this other contour is related to the Stokes automorphism. If s of theta plus of phi tilde is equal to s of theta minus of phi tilde, this means that the Stokes automorphism is trivial. Is just the identity. So this is called a resurgence constant, and this means that theta is not a singular direction. At this point, you see, this Stokes automorphism connects from above the cut to below the cut. So the way to understand how this Stokes the automorphism is related to the alien derivative is in the same sense in which, how do I connect? I want to connect a function, let's say f of x, with f of x plus 1. Well, you know what to do. You need to use the shift operator. The shift operator connects the function to the function of x plus 1. However, the shift operator can be thought as the exponential of the derivative. This paralleling here is exactly the same between the Stokes automorphism, which is going to be this object here connecting the two sides, and the alien derivative. So we write Stokes automorphism as e to the delta. So this connects between two, well, they connect across a singular direction. Is Stokes direction. The logarithm of the Stokes automorphism, it's called the alien derivative. And it's in the same spirit as the Stokes automorphism acts as a shift operator. The log of the shift operator is the standard derivative. I will not give you the most general definition of the alien derivative, just because, first of all, I don't need it, and secondly, because it's easier to give you some examples. However, the key idea is this one. If I pick my favorite singular direction, I want to connect across this direction, and I need to use the Stokes automorphism. I can write this one as the exponential of a collection of derivatives. I need to take all the singular points in this direction. So let me say gamma theta is the subset of gamma with singularities in the direction theta. And then I write it as e to the minus omega z times this alien derivative delta. So from the Stokes automorphism that we wrote before, it's a little exercise to expand this exponential. So we see that the Stokes automorphism equation that I wrote before can be rewritten in terms of its log in this way. If I integrate from above, is the same as integrating from below, plus a bunch of other stuff. Sum from 1 to infinity, sum from n1, nk bigger or equal than 1, e to the minus omega 1 plus omega n k z over k factorial. This is just coming from the expansion of the exponential. And then the raised summation along the direction minus of all these alien derivatives, which I haven't told you yet what they are. Good. So before saying some more about this alien derivative, let me just give you an example to see precisely what is going on. So let us consider an example in which the set of singularities is very simple. It's just a single point. And let us also take that the simple pole structure, the simple singularity structure holds everywhere in the complex plane minus this point. So I'm assuming that the Borel transform is literally alpha divided by 2 pi I t minus w plus 1 over 2 pi I phi hat t minus w log of t minus w. I'm assuming that this holds on the whole complex plane minus the pole. So this is the Borel plane. This is the singular direction. This is omega. And now we want to integrate in these two different directions. So this is a slightly more difficult exercise, but hopefully it should not be really that hard. You can actually do this integral. The pole is simple, the log is slightly less simple. So we want to compute this difference. And I'm claiming that this difference is alpha e to the minus omega z plus e to the minus omega z times the integral between 0 and infinity e to the minus z of t times the minor of t in dt. However, we know already the expression from before. The difference in these resummations should be given by a collection of alien derivatives. But in this case, we only have a single singular point. So this difference should be equal to the exponential minus z, the resummation along the minus direction of the alien derivative of this function. So from which you can conclude that this alien derivative in this simple case is nothing but the singular part. Is alpha plus phi tilde z, or equivalently in the Borel world, alpha delta plus the minor. So the singularity structure of the Borel transform is captured by, okay, a constant, but another asymptotic formal power series. And the difference in resummation, as you have seen over and over during this course, is exponentially suppressed, and it carries information about this other singularity. As a slightly more difficult example or exercise for the students, consider the following formal power series. Z is A divided by Z omega plus A plus B minus C over Z omega squared. These first two terms are just so that I don't have anything floating around that don't really matter. So remember, it's always the tail of the series that dictates everything important. So the tail of the series is the asymptotic expansion n factorial over Z omega, the n plus 1. So we start with a pure factorial growth, and now we perturb it slightly. A plus B divided by n plus c divided by n minus 1, which is a combination that we've already seen appearing in Gerald's lectures. So I start with something that is factorial, plus 1 over n factorial, plus 1 over n minus 1 factorial, with a, b, c, and omega complex numbers. And let's avoid 0. So it's not trivial. I claim, and this is an exercise for you. What I wrote in my notes is false, so I would, well, I can easily compute this one instead of telling you what it is. What I wrote is incorrect. Compute this. You will see that in this case, you're gonna get an expression of this form with a very well-defined minor. Okay. Oh no, perhaps actually what I wrote is correct. So let me write it in here. Well, check for you, not sure. It should be minus 2 pi I a plus b over omega z plus c over omega z squared. Not 100% sure. Good. So in this case, the story is simple because you see I'm starting with something that, although is not purely factorial, is not that far from that. It's n factorial, 1 over n minus 1, and so on. But in general, you're not gonna just have a purely factorial growth. So you cannot assume that the simple singularity structures hold everywhere. This is a local statement. Your function is defined on a multi-ramified Riemann surface. So the definition of the alien derivative is more complicated. So I would suggest you to go through David Sozin lectures, which are really nice and very thorough. So over there, there is the proper definition. So the idea is that when you want to reach a singular point in a certain direction, you kind of average over all the paths reaching that point and passing through a bunch of singularities. However, I don't want to give you the actual definition because we're not going to use it. We're going to do something else later on. But just to conclude, well, yes, today's lecture, let me give you some properties of this object. And we're going to be using it tomorrow. So as the name suggests, it's called an alien derivative. It is a derivative. It is a derivation with respect to the appropriate product. So it is a derivation in the sense that if you take the convolution of two guys, it distributes and similarly in the multiplicative model. If you take the product of two formal power series, it's just distributing. Secondly, it does not quite commute with the derivative with respect to z. If you take the derivative with respect to z of your favorite formal power series, Gevrey-1, blah, 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 and you compute the alien derivative, this is equal to the derivative of the alien derivative minus omega. So you have this new extra term. So if you wish, the commutator between these two is given by this object. And this is another exercise that you can check concretely. Exercise number 10. Check this last property for exercise 9. So I gave you a very simple formal power series in here. First of all, take the derivative with respect to z, redo the Borel summation, study the singularity structure, compute the alien derivative, or compute the right-hand side of this last property. And you will see that the two things match. This last property tells us that there is actually a slightly better object to use compared to the alien derivative. So we can introduce what is called the dotted alien derivative, which is e to the minus omega z delta of omega. So that with this definition, the dotted derivative does commute with the standard derivative. However, at this point, we really need to extend our alphabet. So there are some really nice lecture notes by Edgar on trans-series. So I'm not going to give you the most general version because we don't need it. However, you see that at this stage, I'm introducing this new symbol, e to the minus omega z. This object does not exist as a formal power series. It's something else. You cannot expand this object when z goes to infinity. So this means that we need to introduce a new object in our formal power series. So if you wish, we can introduce a certain grading on this formal power series. So e to the minus omega z, new symbol. So we want to extend, we can extend our resurgent functions of formal power series by considering these resurgent functions as asymptotic formal power series, but graded with these exponential suppressions. So what it means in practice is that you're studying object of this form, phi 1 tilde of z plus e to the minus omega 1 z phi 2 tilde of z plus e to the minus omega 2 z phi 3 tilde z plus dot dot dot. And these are objects that we have seen over and over and over during this school. So this is an example of what is called a trans-series. Is not the most general trans-series possible. As Gotche already mentioned today, for example, the easiest thing that you can see in here is that we don't have any log. Log z is another beast that is new. It cannot be expanded, and is not z, and is not e to the minus z. So in quantum mechanics, you can get away with log z or log h bar, and e to the minus 1 over h bar. However, these are what are called height 1. So you don't consider e to the z, and depth 1. You don't consider log of log of log of log. But for what I'm going to be saying next, this is going to be enough. So at this point, what we want to study are objects of this form in here. And I can say I have a little bit more time, so let me say a few more words before we stop. It's probably a good stage to stop before introducing the bridge equation. So at this point, let me note the following. The full knowledge of a resurgent function comes when we know all the alien derivatives. Comes from knowing all its alien derivatives. It is not enough to say, so if you say that delta omega of phi tilde is equal to 0, you cannot conclude that omega is a regular point. You need to know all the alien derivatives. And this is a good final exercise before I stop. So let me consider two guys that we studied yesterday. 1 over t1 minus 1 by 2 of t 1 over t minus omega 2. And let me assume that omega 1 is different from omega 2. So these are two very simple examples of, I think you can still hear me, but my headphones died. This is a very simple example of two simple resurgent functions. They are just poles, which means pure factorial growth. Yesterday, few of us have computed this object in here, which had a new pole at ω1 plus ω2 and log singularities. So at this point, the first part of the exercise, that should be fairly simple from the definition I gave you above. Compute the alien derivative of phi1, and you're going to find 2 pi I delta. And then compute delta over 2 phi 2, and you're going to find 2 pi I delta. Delta omega phi 1 is equal to delta omega. Well, let me write them separately. Is equal to 0 for every omega different from omega 1. Phi 1 is regular for all the points except omega 1. Delta omega phi 2 is equal to 0 for all the points different from omega 2. At this point, you can compute this object, delta of omega 1 plus omega 2, on the convolution product. The first thing that I want you to use are the properties of the convolution and the delta to show that this object must vanish. However, we know already from yesterday that omega 1 plus omega 2 is not a irregular point. So from here, you would be wrong in deducing that omega 1 plus omega 2 is regular for the convolution. How would you see it? Final part of the exercise. Compute delta omega 1, delta omega 2 of the convolution. And you will see that this object is equal to something which is not 0. So you see that just because you get to a point, the point omega 1 plus omega 2, you should actually check all the possible ways of reaching that point. In this case, we went directly there and we saw that the alien derivative was vanishing. However, there is another possible combination, which is this one, which is not vanishing. We know that this is not a regular point. We computed yesterday this convolution, and we knew that there was a simple pole there. Good. So at this point, the next thing that we want to use this machinery to actually see how to implement a trans-series expansion of some prototypical differential equation. And we're going to find a way to connect the standard calculus, really differential equations, with this alien calculus. And this goes via what is called the bridge equation that draws a bridge between alien and standard calculus. But all of this is going to happen tomorrow. Good.
Okay. Thank you very much for this second lecture. Are there any questions, comments? Something, see a comment on the chat. There's a comment from Ovidio Costa.
Thank you. Yes, short comment, but maybe it was clear. This is not a discontinuity of the resum function. Thank you so much, but a discontinuity of the resummation and not and of the trans-series. Thank you so much. Absolutely. Yeah. Yes. Yes.
Yeah. Any other comments, questions? Let me check for.
There is something.
Yeah, there's a question here. What was the reference you mentioned?
Oh, excellent. I wrote it yesterday. Let me rewrite it again in here because I have all my notes. Of course, all of us are working from home, which means that we are slowly expanding our domain over the whole table. And I'm not going to show you the table because it's a mess, but I found what I wanted. So the reference I was talking about is David Sozin. 1405 times 0356. Incidentally, David was giving, I guess it was like probably related to some of these topics when I was an undergrad in Pisa, but at the time I was studying electromagnetism. So I remember seeing this title, I think it must have been something like Resurgence and Dynamical System. And I thought, okay, yeah, I'm not gonna go to any of these lectures. And now in hindsight, I wish I went there.
So are there any other questions or comments? Too bad from David.
Yes.
He says.
Perfect.
Oh yeah, there was a raised hand here.
Yeah.
Oh no, I missed. Sorry. I was going to. Yeah, I don't know what happened. There was a raised hand, but then it disappeared. So maybe it wasn't. Okay, I don't see anything. Q&A or the chat. Well, again, there will be probably time.
Yeah. So we are going to the tutorials anyway now. So
yeah.
Sharing.
So again, thank you very much to Daniele and to all the speakers for this session. I think it was really interesting. Again, very interesting combination of topics too. And I think there's a link to the tutorial session that starts, well, maybe in 5